And it's my pleasure to introduce our next panel, which is Ideas to Flight. And there's a brief video intro. So thank you all for listening. Bye.
What was your spark of inspiration that led you to aviation?
There really is no substitute for taking an experiment to flight. You learn things that sometimes you don't want to learn, but you also see the beauty of the real atmosphere and the challenges that are associated with real vehicles being flown by real systems and real pilots.
You guys ready to turn in again for a partial?
Join us at NASA Armstrong, and let's find a way to bring your ideas to flight.
How about that video? Man, this is a great day. Welcome to our panel discussion about bringing ideas to flight. Today's theme is about turning thought leadership into action, and we brought together a panel of NASA leaders who are responsible for doing just that, but each in their own way. Each of our panelists is an expert in conducting research using a different capability: computational analysis, simulations, ground testing, and flight testing. Now, capabilities are not just buildings, computers, or aircraft. They are the facilities, the technology, and most importantly, the people who together accomplish the mission. In our case, innovative research to transform aviation. First, we form the hypothesis, identify the questions that we're asking. Then, we consider using the capabilities best suited to advance our knowledge based on the questions we're asking and the outcomes we're seeking at each stage in the development process. Today, our panelists will talk about how they use their capabilities to make discoveries, to buy down the risk in mature technology. Let's meet our panelists. First, introducing myself, I'm John Montgomery, and Deputy Associate Administrator for Policy at the NASA Aeronautics Research Mission Directorate. I lead our efforts to make sure we have the right facilities, technology, and people to stay at the forefront of aeronautics technology development. Dr. Shada Hosseini is an Assistant Project Manager for the Transformational Tools and Technologies Project at NASA Aeronautics. Shada works primarily in the areas of applied computational fluid dynamics with an emphasis on aeronautical technologies. Diana Acosta has enjoyed her adventures in supporting aeronautics research, human exploration, and space technology development at NASA for nearly 2 decades. Currently, Diana is Chief of the Aerospace Simulation Research and Development Branch at Ames Research Center. Steve Helland is the Associate Director and Technical Advisor for NASA's Aerosciences Evaluation and Test Capability portfolio, who manages large ground test facilities across NASA Ames, Glenn, and Langley. And Steve has a master's in electrical engineering. Nils Larsen has been a test pilot for nearly 30 years with the Air Force and NASA, and currently one of NASA's project test pilots on the X-59. Also, he's NASA's Senior Advisor for Aeroflight Research, trying to help to get your ideas to flight. We'll start off today with each leader describing in a few words their capability, how it's used, and maybe some strengths or shortcomings. So Shada, first to you.
Hi, thank you, John. All right, so my background is computational fluid dynamics, or it stands, or in short, CFD, which uses physics-based mathematical modeling and helps us to numerically solve for fluid behavior So we use computational methods in order to study airplanes, cars, rockets, or even blood veins, because they all operate in a fluidic environment. So when we use CFD, it's upfront when we have a problem sometimes, and then throughout the design cycle, and afterwards when we want to improve some of our operational practices. And we use it upfront because it can enable us to take a look at physical properties without investing so much time and money in assessing some ideas we have. And then working with our colleagues in an iterative process in wind tunnel, flight, and other capabilities, we can go back, assess some of our design choices, and make sure that the design assessments we make are correct. Computational methods can also be very powerful when we are doing accident investigations, for example. In the case of Columbia disaster, CFD helped us to create this database that we could look at the probability of having the bipod ramp foam hitting the wing leading edge, and that really helped us understand what happened on that accident, the day of the accident. So with CFD, you mentioned what are some of the strengths and weaknesses. I can say that the main strength is that quick capability that we can use to assess some technologies, and then also perform some of the freer simulations, for example. On the other hand, performing dynamic simulations, having flight maneuvers in CFD is not as easy. And after all, CFD is a model, right? And we need our colleagues from other disciplines to validate our models. And that's why it's critical for us to work together in order to have a comprehensive engineering practice.
Thank you, Shada. And I'll take the moment just to note there is a comment in there, a question in the chat, which I think is actually pretty helpful to help folks understand. So what kind of software is used for CFD? Can you just like buy it in a store or download it somewhere? Or it's a little bit more custom than that, I think.
Right. So CFD, again, computation is a physics-based mathematical models. So depending on the problem we have, given the limited computational power we have to make some assumptions to simplify the problems. And in some scenarios, we use very theoretical problem, like very theoretical equations that you can even write a few lines of MATLAB code or Python code on your laptop to solve it. As the problem gets more complicated, we have to bring in more terms to account for physics better. In some scenarios, we can neglect some viscous forces. So we use some Euler equations. At NASA, we have been developing a lot of different fidelity of softwares that we can use. And as the problems, again, get harder and harder, we bring in terms to account for more physical phenomena, such as turbulence fluctuations and all that. So in modern world, I would call CFD to be a software that you can use, but also as the problem gets simplified, we can all write our own simple codes that we can use on our own personal laptops.
All right, great. Thank you, Shada. All right, let's go to you, Diana. Talk a little bit about simulation.
Yeah, so simulation is really fun, and I think it's going to be relatable to the folks on this this event. And I'm kind of curious, so pop into YouTube and drop in the chat if you've ever participated in or seen a video game. Because the simulation is very much like a video game. We are modeling something that is quite real. And also, our imagination of what the future is going to be is something that we can bring into a simulation. The difference between a video game and what we do for aviation, of course, is that we use simulation for engineering purposes. We are looking to learn and reduce the risk of taking this future that we've imagined and bringing it into reality. So we stitch together all the pieces. Shada was talking about being able to increase the fidelity of those analyses as things mature. We do the same thing in simulation. So the pieces that go in are those mathematical models. Shada used the term physics-based mathematical models, and the data that she's generating is going into the models of the aircraft, either a single aircraft or multiple aircraft that we can model. We're possibly adding the people, whether they're pilots, operators, controllers, passengers. We have the interactions between the aircraft and the people, the procedures, and all the technology that supports this. And depending on how we target those different pieces and how relevant they are to either reality or that imagined future, we can support the engineering process throughout that life cycle, from early design exploration and development, maturing technology, on through testing to see if we met performance expectations or what stakeholders wanted, what the company wanted, what passengers want. We can use simulation to check on that. And then when we get towards operations, of course, drive down risks, really focus, have reality into simulation in a way that's important to say, this is going to be safe. Our pilots know what they're doing. They are trained. The operators, they are trained. Controllers, they are trained. And any anomalies we find in flight, we can back to simulation and drive out what we need to do to go back to flight safely.
So you're really seeing that future state is a real strength of that simulation, isn't it?
Absolutely. If we can imagine it, then we can model it or we can practice it in simulation in what hopefully is a cost-effective way and also a very safe way, and all reducing the risk of that future. If that makes sense for what the development is trying to achieve.
Great. Yes, thanks, Diana. All right, Steve, talk a little bit about ground test.
Yeah, and it's a great segue from Shada and Diana from the standpoint you've done all your homework up front in design, and now we've got to kind of see whether or not the models are correct. And I think this addresses one of the questions in there as far as accuracy goes. So for us, we've got wind tunnels that are big and small. They've been built many years ago. We have lots of things to reduce the flight risk. Computational validation, as Shada mentioned, that's one of our roles, and to do some fundamental research. We've got really unique measurement techniques, and it measures, we try not to be very disturbing in the flow of the wind tunnels, so that way we can get accuracy and be as close to reality as we can. But I want to point out that our workforce has a unique skill set. You know, they have degrees in aerospace and electrical and mechanical engineering, but they also couple that with a lot of hands-on experience. So we've got a cool workforce from that standpoint. CFD and simulation definitely affect what types of testing that happen in our ground test facilities and how that sets up. And it's kind of one of those pathways and for us to minimize the risk to flight. So one of the things John had mentioned about examples. So from a TRL standpoint, test readiness level, you know, post shuttle, we were thinking from a NASA perspective, what could we do next? What might be the next one? So there was kind of a proof of concept, and I worked on an orbital space plane. And at that point, it was just not feasible to put some sort of wing body on the front end of a rocket because the lifting was so separated. So that was one of those, hey, let's try it and see if it works. But then to another degree, we were doing a fighter jet, and the company that was testing in our wind tunnel, based on the results of our wind tunnel data, they made a flight line change. And Nils, you have to correct me whether I use the right terminology from that standpoint, but they had an aircraft already built. Because of the results that they found out, they did some changes on the actual aircraft to do that. So it kind of gives you that spectrum of early concept to really, really impacting things in the flight regime. And it's really a nice way for us to kind of work that and validate what's been done in Shada's world as well as Diana, and it's a natural step to the next person.
Thanks, Steve. So one question for you. So do you have a whole airplane in that wind tunnel, or how does that work?
So depending on the audience and everything, it's a miniaturized version. We call it scaled models. So it's a smaller one. And folks that are far smarter than I am, they decide what that optimal size is based on the size of the test section that we're using. So they are subscale. Although I have to put a caveat that we do have one tunnel that's run by the Air Force. They put full scale aircraft in them. And I'm not saying that you can't do that in some of the wind tunnels, but in most of the ones we have, they're subscale.
Great. Thanks for saying that, Steve. And our last panelist, Nils, talk a little bit about bringing to flight. What's that capability?
Well, flight test is kind of like the ultimate, it's the real thing. We've used the word model frequently, and sometimes it actually is a model in flight test as well. But you're now dealing with the real atmosphere, usually, real hardware, real software. You're in the ultimate environment that you're doing your design for. A lot of times people think, when you think about flight test, you think it's at the end of that chain that we just have been talking about, that it goes to CFD and it goes to simulation and it goes to the tunnel. And frequently that can be the way it is. Like if you look at X-59, there's a lot of examples of how that has progressed, but that's not necessarily always true. Sometimes you can actually do flight test at a much lower TRL level, even down in the, 3s, 4s, 5s, kind of thing, and get, early looks at data. One of the other things that you'll see sometimes is that iterative process back and forth between us and CFD or us in the tunnel, us in simulation. When it comes back and forth, you see that almost all the time. It's rare that any one of us really plays all by themselves. Some of the lower TRL stuff that you might think about is things like going out and doing emissions testing, or looking at early model validations, different levels of autonomy. If you have some form of an autonomy research platform, that's maybe optionally piloted or something like that, you can look at earlier TRL levels, than sometimes you might not think of when you think of us at the end of the chain, because we're not always there. It's kind of funny. People look at me and I fly F-18s and F-15s. They said, what are you testing on that? That thing's been around for, longer than many of the people watching this panel today. And we just always kind of joke and we say, we're using yesterday's aircraft to test tomorrow's technologies. One of the great examples is one of our F-15s. We can hang stuff on the bottom of it, and it's kind of the ultimate wind tunnel. So it is a model that's hanging on the bottom. It might be an inlet. It might be a wing design. It might have been in one of the other tunnels before it got to us. And then we can go drag it out in the real atmosphere and, go out and get that data in the real atmosphere for longer durations, multiple altitudes and a lot of different stuff. So there's a lot of different things you can do, throughout that TRL, levels that are out there. But, flight test is a lot of fun.
It sure sounds like a lot of fun. And I loved seeing all the great equipment that you have out there at Armstrong Flight Research Center, because you have both the vehicles that are being tested themselves or maybe flown, but then you have the chase aircraft as you described. So really it's sort of a system of capabilities together that make up flight research capability.
Yeah, and if you think about it, flight test doesn't have to be something like an X-59 or an F-18 or a King Air. It can be a small UAS. It can be something as small as your hand or potentially even smaller. Once you start talking about that, there's the whole gambit of what you can do, when it comes to the size of these vehicles.
So I've picked up from the explanations that you've each offered that some of the magic here really is in how these different capabilities work together, and how that really provides really solid understanding. So I'd open it up to the panelists to offer some additional thoughts about that synergy or interaction that they see between their capability and the others here.
Well, I can give an example that I can think of in some of our stuff. Frequently, we will have something that has played in CFD early look, for a new design that they're going to go put in the tunnel. Then the tunnel will then go and they'll run whatever this model is that they've built. I think one of these examples would be, I think it was a supersonic boundary layer transition. I think another one was swept wing laminar flow, something like that. So those ended up, playing in CFD, move to the tunnel, and then the tunnel can turn around, and when they get their data, they go back and they update the CFD model, making it even better whenever they're trying to base their physics now on the tunnel. Then we go put it on the bottom of the airplane. We go out and fly the same thing out in the real atmosphere, and then we can turn around and go back and update that CFD code, making that even better. So that tool is now available, and it is even more accurate when it comes to, the next round when somebody else comes in with an idea, that they're, starting, through all that. So frequently we are always helping each other when it comes to that. And, there's tons of times when it comes to simulation as well. I mean, crap, I've been living in a simulator lately in the X-59, and sometimes it's for training. Many times it's for the development of, say, the flight controls or any number of different things. So, it's an iterative process, that we're all constantly using each other's work and updating, making everything better throughout that chain.
Mhm. And also to add to Neil's point, sometimes also when it comes to certification of an aircraft, we've done CFD work, it matches perfectly with the wind tunnel. We go to flight, something happens. Okay, what is going on here, right? We are doing various flight maneuvers, and then we can see, well, we are not meeting some certification requirements. And that point, CFD can also come in and really help to kind of assess various proposed solutions. We can go back to CFD, look at a lot of solutions because it's fast and quick, right? And then kind of design some flight tests to go to the edges of the envelope. We come back to flight, and then we can see, kind of narrow down our solutions and meet some of those certification requirements. But as Neil suggested and as basically explained, is that it's all iterative, and it's very important to understand that.
Yes.
So we're proving our hypothesis, and we're actually making the tools better as we go.
Yep. Understanding the sensitivities and simulation can help with that, so that if we find an area where we think it's going to be super sensitive, make sure we got it right from analysis or ground data, and make sure we're super careful when we're expanding that flight envelope and flying in new regions, trying new things. And the interaction is super powerful within all these capabilities.
So we use them across our portfolio, but since we're talking today about putting leadership into action, let's focus on the action. So we'll dig into one area of research and illustrate specifically how these capabilities have been used. And let's target advancing state-of-the-art in supersonics. Now, I know each of us have something we can put up behind us or show on the screen as an example. So maybe we'll go first to you, Shada, and maybe you can talk a little bit about how CFD has helped us with our supersonics research.
Absolutely. So one of the major questions we had going into X-59 was that, can we design a jet with a noise signature of less than 75 dB? 75 dB, right? So then to answer this question, we've used CFD extensively on the design part of the vehicle here. As you can see this video, there are various design features on this vehicle that has been enabled by CFD to achieve that low boom characteristics. This needle like nose, the flat bottom of the fuselage, the tail. So on the design aspect, CFD has helped with aero shaping the vehicle. At NASA, the highest level goal of CFD was to mature tools and technologies to get better at predicting ground noise level. And that had two fronts, basically. So looking at the flow physics near body, so that is around 5 body length away, and having the capability to predict how these pressure waves are developed and propagate to that boundary. And then using another propagation software that takes that near body predicted pressure and marches it down to the ground in time and space to basically see what happens when you're close to the ground level, and then translate that to the acoustics. And over the years, we've matured our technologies on the computational meshing side. We've improved our turbulence modeling, our schemes, such that now if you take any geometry, supersonic, and give it to various groups within NASA and ask them to predict the ground noise level, the predicted values are pretty similar. They're 1 to 2 dBs different, whereas a few years ago, we were 5 to 10. On top of that, in T-Cubed, we have been investing money and effort into basically look at uncertainty quantifications, because with all these predictions and modeling, there is some sort of uncertainty associated. In addition, on top of that, we have atmospheric uncertainties. So when you kind of bring both of these together, what does that translate into the uncertainty we have in the predicted ground noise level? And it's been through these type of maturities that we have been enabling in our tools that now CFD has enabled us to create this large matrix of data, looking at various scenarios of running or operating this vehicle, so that it can be basically provided to a flight planning software, so that as a user, as a pilot, you can go and put in the operational conditions, You can put in basically the desired ground noise level, and then the software can help you come up with a flight path, saying, for example, suggesting at what altitude to fly the plane, how should the control surfaces to be positioned. And that's how powerful CFD can be when it comes to practical sense. And you can kind of see it go from the up front, from the design all the way to the operations.
So that's great. Really, really comprehensive use of that tool throughout the envelope of research. That's great to understand. All right. So Diana, how's simulation been used to help us with supersonics research?
Yeah, let's queue up a couple photos, and we will see Niels's home away from home. He admitted he's been living in a simulation recently, and this is one of those simulators. This is one at NASA that we are using to mature the control system for the flight of the X-59, and also something that we call handling qualities, which are our measurement of how well this vehicle is going to perform its mission and how easy is it for the pilot to achieve that mission throughout that process. The fun part about tuning the flight control system and the handling qualities are that with an X-plane, we have superheroes like Niels as test pilots who are going to be flying these vehicles. And so it doesn't have to be perfect, but it does have to be good enough. And so simulation is a critical path to reducing the risk for the flight controls and handling qualities. Another piece that has been critical is providing the tools and technologies for the pilot to successfully fly. And if we go to the next chart, we'll see a simulation that has an external vision system. This is a vision system that Niels has flown, and he can talk about that if he decides to. It has gone to flight, and it is integrated into the X-59 for when that flight happens. In simulation, however, they did the design and development of what it would be like for the pilot to be able to see out the window through a computer screen that is streaming from cameras that are attached to the airframe. So this is a simulation. That long nose of the X-59 and the placement of the pilot make it really hard to look outside the window. So the pilot needs that visibility. And we found that the screens here that were simulated and then flight tested later are giving the pilots enough visibility, sometimes even better than just looking out the window. So lot of contributions in simulation, and I hope a lot of fun. Niels can tell us what home away from home feels like for reals.
So that truly is the best kind of heads-up display. It's actually using that as your screen in front of the aircraft. That's great. Hey, Steve, welcome back. We lost you for a minute there, but glad to have you. But just in time, can you talk a little bit about supersonics and ground test capabilities?
Yeah, so that's a perfect setup for now we're starting to look a little bit relative to the scale models that we put in the wind tunnel. If we could show the first one at Ames Research Center. This one is relatively small, and I think a lot of it is we move through the different aspects that we're testing in the speed regime. We're looking at signatures around sound and acoustics, as we call it, and then also looking at some dynamics and stability. If you look at the next slide, now you're looking at a little bigger model. It's a little bigger one, and this is in a transonic tunnel at the Glenn Research Center. As you notice, is scaled up. What we do in the different tunnels is we measure different aspects. So as we're looking at it, maybe we're looking at the nose, maybe we're looking at the interaction of the wings. How do the different interactions across this new body are going to work? And we take, there's no doubt all the simulation and all the CFD work that's done influences how the model is built, how we position it in the tunnel, and how we take the specific data that we're taking. And the last photo I have is some of the flow visualization techniques that people are using. We do a lot of, what do we call it? Optical measurements. That's the term I'm looking for. To measure different flow patterns across the vehicle into subscale. So it's really important for us to do that and get different information so that when Niels gets up and he's flying in the aircraft, there's little, quite honestly, there's just less gotchas, less surprises for him that he has to use his flight experience and maneuver around. But we do a lot of work in that area, and And that's a key role. I think wind tunnels for us we're on the critical path. It's an important piece for us to get to flight. And we're always honored to be a part of that.
That's great to really see that progression from that early stage all the way to later stage. So then the final stage is getting into the cockpit. Although you shared with us, Nils, already that you used flight already in early stages. Can you talk a bit about the different ways that you used flight for our supersonics research?
Sure. There's a ton of different things that we do, throughout the time that we do, or since I've ever been at NASA here for whatever it's been, 17 years. All the stuff that's kind of led up to X-59 and Quest over the years. We had a sonic boom demonstrator. We had a program called Quiet Spike. Both of those looked at shaping the airplane for the forward shock. We had a program called Landsets where we looked at the aft shock on the airplane. We've looked at various ways that the shock waves and the boom moves through the atmosphere over the years through programs like SCAMP and Carpet Diem. And, we like to make up all these fun names for all these. We've perfected some airborne Schlieren techniques so that we can actually see the shocks in the airplane. Sometimes we even feed those back to our CFDers and kind of say, hey, look, there's a shock here. Well, we didn't find that. And then they go figure out how they can make their, computer models better so that they can figure out why it is there that shock there. So you see a lot of this stuff over the years, and one of the big reasons why we have X-59 is we had done a lot of work. And now it was time to go out and see how do we go out and just shape the whole aircraft. And a lot of the technologies that we had worked on before were actually for ground test. It was the microphones and how are we going to record all these sonic thumps or sonic booms that are made from, normal supersonic airplanes or the X-59. So a lot of different technology developments throughout there. One of the big things that I've always seen and I thought was just fascinating as I've played, with this is watching the people, the CFD, and then it goes to the aero model and they're building the flight controls. And then we have our friends in the wind tunnel. They take their data and then they feed that back into the aero model because, we're constantly tweaking that, which now makes us have to tweak the flight controls. Oh, by the way, we're using the simulators that whole time, for us to go and do piloted simulation as well as non-piloted simulation to go and improve the flight controls, so that when we go to first flight, it's not going to be a surprise when it's time to go fly that airplane. But it's that we talked about that iterative process before. We're constantly looping everything back and everybody's got a part to play in this. I think I have the best seat, but they would probably argue with me because they love their jobs too.
Yeah. Well, it really is a team approach and really is, I think, a legacy of great collaboration across these different capabilities to get to where we are now with this X-59. Of course, there's still more to be done, right? There are more challenges remaining before we see introduction of commercial supersonic flight. If it's going to be part of our future air transportation system, it's got to be sustainable. We must make strides to increase our fuel efficiency, reduce airport noise and aircraft emissions. We need safe integration of these fast aircraft with the slower aircraft all working together in the safe airspace. And at NASA, we're pursuing key knowledge required for sustainable travel, really at any speed. But looking to the future, what's next? How do you see NASA's use of these capabilities evolving? Diana, how about you? How do you see simulation evolving?
Well, I don't know how much it's going to evolve as how much we're going to be able to embrace simulation to really answer some of the hard questions. There's a lot of challenges, as you just mentioned, a whole bunch of them for bringing a supersonics vehicle or any of these new concept vehicles into the aviation market and helping businesses be successful to make a profit and get people or cargo where they need to go. And we need to go about that. It's a pretty challenging path. We need to go about that with confidence. So simulation is that, and so many of the facilities and capabilities that we're talking about today are those abilities to reduce the risk and go forward with confidence. So whether it be helping to have confidence in the flight control systems or the handling qualities of a new vehicle, that's key for all of these capabilities, including simulation, of course, which is a pretty great place to work, by the way. And also that integration into the airspace. You know, we talked about X-59 being one vehicle, and we have been simulating one vehicle and developing technologies for that one vehicle to be able to interact with other vehicles. But yeah, when we start putting a supersonic vehicle or any super slow vehicles together, then that's going to get to be a fun day. And we need the operators and controllers who are responsible for that to have confidence that they can do this as we're investing in the technology, as we're investing in the design and development and going to market with these capabilities. So looking forward to simulation being part of that critical path and growing and evolving in a way to do that in support of everyone out there.
Really helping with some of those other transformations we're working on in addition to supersonics.
Absolutely.
Right?
Absolutely.
Yeah. All right, Stephen, any thoughts on your thoughts?
Yeah, I think it's a big area for us. You know, technology is changing. As Diana said, what are the challenges going forward and how do we play that role? I think, you know, Shada, their CFD computation, you know, computers, my phone has more computing power than my first computer ever had. And those sort of things, as that advances, it focuses our area around ground testing a little bit more tighter, in a tighter realm. And where do we really need to do that? So honestly, you know, our capabilities that you see today, it's going to be different. It's going to be different with, I'll throw out words like autonomy. Some of the way we've got optical measurements. A lot of our wind tunnels have solid walls, and there's just not the ability to measure those things. And, you know, and the big one everybody's talking about is AI. How is that going to influence our testing ability and how we're going to go about that? And how do we use it to our advantage to be smarter testers? Where in the past we used to be able to take lots of data and do a lot of things, but the demand is pretty high. So we need to approach it really from a smart perspective. So I see things really drastically, not just hardware, but just the way we do testing will be different. And the role in which we play may change as well.
It's a great point, Steve. And that is one of the questions in the chat. So I'm curious, anybody else have thoughts about how AI might impact their area of research capability?
So quick thing on the CFD. So with machine learning or artificial intelligence, it can become powerful when we are doing interpolations. For extrapolation, we still, I think, would need to do more CFD or actual testing. But when we do interpolation, it can really reduce the number of cases we run. So it can help us reach the answers faster. And now that moving forward, for example, with having more efficient algorithms or more efficient computing, rather going from CPU based to GPU based, what makes me excited is that moving forward with CFD or computation, we can be answering some of the questions that traditionally would have been difficult. Address some of those flow physics that would be very challenging to address today with the tools we have, may not be as challenging in the next decade or so, or even a few years from now. And that can really help us, again, reach the answers faster.
I think you're going to see AI in a lot of autonomy and obviously big data, and trying to sort through all the data, trying to figure out, you know, what the important pieces are when you have all that data. But I think autonomy, things maybe like, autonomous co-pilot or that kind of thing. AI, we've been using, I mean, AI is not new to NASA, is not new to flight tests, is not new to most of the, you know, people here. We've been using it for years. We've had neural networks and things like that were, you know, flight controls, you know, in simulation, and also on in-flight simulators. That's another big one that, you know, you will probably see more of in the future, you know, predicting you know, trajectories, all that kind of thing. So I think, you know, AI definitely has, you know, a big portfolio here for us.
Yeah, really is. The future of aviation is going to really leverage these tools, both in research, but also even in operation.
Yes.
All right. So I'm about to wrap up the panel. So Nils, I'm going to give you the last word. So the X-59, man, it's just around the corner. Tell us what excites you about what's coming for X-59 and for NASA.
Well, you saw the picture earlier, all the fun stuff I've gotten to do, for my 30 years of flight test and another, well, going to at least 10 years before that of, stuff that I did in the Air Force and beyond. But, for me, this is a culmination of, everything I've gotten to do, flying as a test pilot, flying an X-plane. Well, that's the dream right there. So it's getting pretty exciting. I mean, I've got to see the airplane ever since it was, a little hunk of metal, as it's grown and played in the various simulators from the XVS stuff all the way out there at Langley to, the software integration labs that's over at Lockheed and Palmdale, or our own sims. And I think we're on our third iteration of the simulator that we have here. So, it's feeling more and more real all the time. And with rollout just last month, that was very special. I'll have to say, when they dropped the curtain, I just seen the airplane 2 days earlier. What was the big deal? But when they dropped the curtain, I got a little misty, I have to say, because it was getting real. You could look there and go, there's the airplane. You can see in one of those pictures, there's me strapped into it. It's feeling real. We're in progress, going through ground checks right now. We have an airworthiness review, our FRR. It's not a first flight review. It's more of an airworthiness review that's coming up just around the corner in a couple of weeks. We have impending engine run taxi coming up, so it's starting to get to be the stuff that, makes it really feel real. Like I said, I've been living in a simulator. So it's been, one of those things where I think I've spent like 10 or more hours a week lately in there. So it's been very fun working with a great bunch of people between, the contractors there at Lockheed and the NASA folks and our subcontractors with GE and everyone else. A lot of talented people. Just amazing to see the thing coming to fruition. It's fun when I have my meetings down there or I'm in the sill to at least walk downstairs and go take a look at the actual airplane. To see it sitting there, on its gear. And I think tomorrow might actually roll out of the production side. I think it's scheduled pretty soon to do that. If it's not the end of this week, I think it's early next week. It's scheduled to roll out to the flight line. So it's been, just awesome. So I encourage everyone to stay tuned for the next panel where my fellow X-59 test pilot, Jim Clueless, and many others that are in the supersonic aerospace industry have a lot to share with you.
Nils, thank you so much for your expertise and sharing your history with us. And I also want to thank all of the other panelists. Man, what a great team we have, really helping us to advance transformation for the entire aerospace industry and, in fact, for the world, helping us get places in a more sustainable way, faster, safer, really leveraging all this great technology that our researchers around the world are coming up with. So Shada, Diana, Steve, Nils, thank you so much for being on the panel. Thank you all for joining us. And we have a video that we're going to share that's going to sort of transition off into our next panel. And with that, my thanks to everybody.